Let's take a look at the ratio test. For the ratio test, we're going to take the ratio of two consecutive terms and then take the limit as k goes to infinity. For here, we're going to notice that our value for r, if it is a fraction, some number between 0 or equal to 0, but less than 1, we find that the series converges. If r is greater than 1, we find that the series diverges. And if r is equal to 1, we find this test inconclusive and we must pick another test in order to determine convergence. One thing I do want to point out is that this test is actually really good for series who have terms with exponents and or factorials. When we're trying to test for convergence, one of the first tests that we should always try is the divergent test. That will let us know if it either diverges right away or if we have to use this ratio test. So let's use the divergent test on example number 5, part A. We have, so we want to take the limit as k goes to infinity of 10 to the k over k factorial. Because we don't know how to take the limit of these, we can use growth rates, and we're going to find that this is equal to 0. So this limit was done by growth rates. Remember that when we find this is equal to 0, we know that our test is inconclusive, so we need to try another test. So let's try the ratio test. The ratio test says for us to take the limit as k goes to infinity, and we're going to use the k plus 1 term, so that's going to be 10 to the k plus 1 over k plus 1 factorial. And we're going to divide that by the original 10 to the k over k factorial. So one of the things that I want to remind you of is that when we're dividing by fractions, it's the same thing as multiplying by the reciprocal. So now we're taking the limit as k goes to infinity of 10 to the k times 10. That's the same thing as 10 to the k plus 1 times k factorial. And at the bottom, we're going to have 10 to the k and k plus 1 times k factorial. So I just want to remind you that when we're looking at k plus 1 factorial, that means we're multiplying k plus 1 and then k minus 1 and then k minus 2, etc., 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 until we get to 1. So we notice that this is the same thing as k factorial. So now you see why I wrote k plus 1 factorial as k plus 1 times k factorial. Now let's try to take our limit. Before we do that, we're going to notice that the 10 to the k crosses out and the k factorials cross out. And now we're just finding our limit, and we're going to find that this limit goes to 0. From there, we can notice that this series actually converges by the ratio test. Now let's do example B. Again, we're going to start with the divergence test. The divergence says to take the limit as k goes to infinity of k to the k over k factorial. In this case, we're going to see that this actually equals to infinity by the growth rates, which means it's not equal to 0, that our series actually diverges. What we can do, however, is to go on ahead and see if the ratio test will give me the same results. So technically, we have decided that this series actually diverges and we're done. But I want to show you that if you decide to skip the divergence test, the ratio test should still give you the same result. So the ratio test says that we're going to find the limit as k goes to infinity of k plus 1 to the k plus 1 over k plus 1 factorial. And then we're going to divide that or multiply by the reciprocal of k factorial over k to the k. So we're going to simplify this. We're still going to find the limit as k goes to infinity. Notice we're going to have k plus 1 to the k times k plus 1. So remember, we would add our two exponents, and that's how we get k plus 1 to the k plus 1 exponent. We still have k factorial at the top. At the bottom, I still have k to the k. I have k plus 1 times k factorial. And then now when I'm simplifying, my k factorials go away, my k plus 1 go away, and we can see that we are finding the limit as k goes to infinity of k plus 1 over k, everybody to the k exponent. And we can see here from one of those limits that I told you needed to just start memorizing that this actually equals to e. And e, remember, is greater than 1. So if that's the case, according to the ratio test, this series diverges. Last but not least, let's try the series in which we have the infinite series of 1 over k. We can again use the divergence test to see if it's going to diverge or not. As k goes to infinity of 1 over k, we find that equal to 0, which means we have an inconclusive test in terms of the divergence test. So we want to go ahead and use the ratio test. So when we do our ratio test, we're going to find the limit as k goes to infinity of 1 over k plus 1 divided by or multiplied by the reciprocal of k. So we find that we're finding the limit as k goes to infinity of k over k plus 1, and we can see that that's going to equal to 1. Because that's equal to 1, this test is inconclusive. Let's take a look at the root test. We're going to find that it's very similar to the ratio test, except the only difference here is we're going to take the limit as k goes to infinity of the nth root of our term. So this is actually really good for those series in which they have a term that has raised to the exponent of n. So let's see if we can do a couple of examples using the root test. Here we see that we have the infinite sum of a polynomial divided by a polynomial to the k term. And again, we can use the divergence test if we like, but then again we have to deal with that k exponent. So let's go ahead and just jump to the root test because it will tell me if it diverges or not. So with that in mind, let's do the limit as k goes to infinity. Remember that's going to be rho, so that's the Greek letter for r, so rho is the limit as k goes to infinity. We're going to take the kth root of that. When we take the kth root of that, we're just going to do 4x squared minus 3 over 7k squared plus 6. And we can take the limit of that and we can see that that's equal to 4/7. And we can see that that's actually less than 1, so this series actually converges. Let's take a look at example B, where we have the infinite sum of 2 to the k over k to the 10th power. Again, we can use the divergence test to see if it diverges. We probably would have to use our growth rates, but just in case we forget to use our divergence test first, we can still let the root test tell us if it diverges or not. So again, I want to show you that I'm going to get the limit as k goes to infinity, and we're taking the kth root of 2 to the k over k to the 10th power. And we can see that I'm going to get the limit as k goes to infinity of 2 at the top, and at the bottom I'm going to have k to the 10th power, and then the kth root is the same thing as our exponential fraction like this. From here, 2 is a constant, so I can take that on the outside, and I'm taking for the limit as k goes to infinity. I would have 1 over k to the 10 over k, so I'm going to bring it to the top. So I'm going to have k to the negative 10 over k. So I'm going to say that that's going to be to the limit as k goes to infinity. I'm going to have k to the 1 over k to the negative 10th power. I did this on purpose because we actually know what the limit of k to the 1 over k is, and that's going to be 2 to the 1 to the negative 10th power, which equals to 2. So what we find here, if that rho is greater than 1, which this case it is, then this series diverges. And we say it diverges by the root test. The last two tests that I want to talk about are the comparison test and the limit comparison test. One figure that might help and kind of realize what these two tests are doing is what they're saying is that if you have a series that converges, and we'll call that A of k, if it converges and you find something smaller, then it must also converge. Now, if you find something bigger, we don't know. It could either converge or diverge. But if we can say that we found a series smaller than A of k, such as B of k, let's say, then we can say that both of them are converging if we know the bigger one is converging. Likewise, if we know that some series is diverging, and we'll call that one A of k, if we know it's diverging and you have something bigger than that, then we know that it also must be diverging. But remember that it has to be bigger. If it's something smaller, we don't know if it's converging or diverging as well. So we can only conclude if it's bigger than the divergent series that we already know. So we're going to find out that we're going to be doing a lot of comparisons with our P series because we know those guys just by looking at them, whether they converge or diverge. And then another one we can use is also the geometric series, especially those that converge, because we know that their common ratio, the absolute value of R, is less than 1. So let's try the comparison test. So let's take a look at example number 7, part 1. What we're going to see is we have the infinite sum of k cubed over the denominator of 2k to the 4th minus 1. So let's go ahead and use the divergence test, and we're just going to take the limit as k goes to infinity of k cubed over 2 to the k to the 4th minus 1. Remember, when we're looking at limits as k goes to infinity, we can kind of ignore that part and just take a look at the highest exponents. And we find that this simplifies to 1 over 2 to the k, and when we take the limit of that as k goes to infinity, we find that equal to 0, which means our test is inconclusive. And that means we need to try another test. So let's use the comparison test. So what we're going to do is we're going to look at our original series, and we're going to compare it to another series that we know. So just like we did our limits here, we're going to compare it to 1 over 2 times k. By the P series test, we know that this guy diverges. So the question is, which one of these is bigger than the other? So what we find is that this one over here, our original guy, is actually going to be bigger than what we're comparing it to. So if that's the case, and by comparison, if this one is smaller and it diverges, then if you find a bigger series, then it also must diverge, which means we can conclude that our original series diverges by the comparison test. Let's take a look at the second example. In our second example, we can also take the divergence test, and it says take the limit as k goes to infinity of the natural log of k over k cubed. And we can see that if we do our infinity, we're going to get infinity over infinity, which means we can use L'Hopital's rule. So let's do that. That means this is the same thing as the limit. As k goes to infinity, I'm going to take the derivative at the top, and we're going to take the derivative at the bottom, and we're going to let it go to infinity. We're going to end up with 0 at the top and infinity at the bottom, which means it's equal to 0, and we're going to find that our divergence test, the divergence test is inconclusive, which means we need to try something else. Or let's try the comparison test. So let's get our original series, and let's compare that to k over k cubed. Now the reason why I'm doing that is that we know that the values of k are actually bigger than the natural log of k. We can see that just by their graphs. So I know that this guy over here is bigger than the one that we're comparing it to our original series. So now we're going to see that this one is the same thing as 1 over k squared. And by the p-series test, we know that 1 over k squared actually converges. And now we have our guy converging, and we have our original series smaller, so it also must converge by comparison. Let's move on to the limit comparison test. So before we start applying the limit comparison test, let's talk a little bit about what kind of results we're getting and when to use what. So what we're going to find is that we're going to get two different series terms, and we're going to make a ratio of them and then take the limit. When we take a limit, we're going to see if we get a number. If we get a finite number, some number between 0 and infinity, but not equal to 0 and not equal to infinity, then whatever my series are doing, then they're both going to be doing the same thing. So we're going to pick a comparison series that either diverges or converges, and if we find the limit L is some finite number, then we know that our original series also converges or diverges, depending on what we chose for the comparison series. And we have special cases. If L does equal to 0, but then we have things that say, well, that means B converges, and the limit is equal to 0, that means B was actually bigger than A, so that means A is inside, so we can see that if B converges, then A converges. Now, if our limit was infinity, that means our top guy is greater than our B, so A is going to be bigger than B, but if we know that B diverges, then we know that the outer one, the bigger one, will also diverge. So notice it's saying the exact same thing as the comparison test, except it's after you take the limit. One last thing I want to mention about the limit comparison test is that it's good for rational functions, as we will see in our example number 8. So let's say we want to find what happens to this series. So we can see that if we use a comparison, so if we were just going to look at what it looks like, we're going to have k to the 4th over 2k to the 6th. And then notice I'm just looking at those with the biggest exponents because that kind of guides what our series is going to look like. We're going to say that our series actually equals to 1 over 2 to the k squared. Let's do this. Let's choose that our original series can be represented by 2 over k squared, and that the one we want to do is 1 over k squared. And we know it converges by the p-series test. But we are guaranteeing that our original series is going to be smaller than that we're comparing it to. Think about it, that if k is equal to 2, let's say, on this side I would have 2 times 2 squared. Over here I'll just have 2 squared. So I have 1/8, and we're comparing that to 1/4. And we're going to see that it's always smaller. So when we're doing that, we're ensuring that the series that we're comparing it to will always be bigger than our original series. Now let's use the limit comparison test. So we're going to take the limit as k goes to infinity, and we're going to get our equation that we're comparing it to, right? 1 over 2 to the k squared. And we're going to divide that by 1 over k squared. When we do that, we're finding the limit as k goes to infinity of k squared over 2k squared. And we're going to find that's equal to 1/2. It is finite, which means because the one that we're comparing it to converges, then this guy must also converge. Let's try example number 2. For this one, we're going to say that this is very similar to 7k squared over k to the 4th. So that is the same thing as 7 over k squared. So let's compare that to 1 over k squared. This is always going to guarantee that our series is actually going to be bigger than the one that we want to compare it to. Remember, the one that we want to compare it to converges by the p-series test. So now let's take the limit as k goes to infinity of 7 over k squared divided by k squared, and we're going to find that our limit is equal to 7. So because our comparison series converges, then our series also converges. And that concludes this video.